Okay, we're ready to talk about section 1.3, and the last two sections we spent a lot of time talking about how to solve systems of equations, and now we're going to spend some time looking at the properties of those solution sets. So this will be important to, just like a sociologist goes into the society and sort of investigates what these people might have in common or what their origins are, we're going to take a look at the solutions to the systems of equations that we now know how to solve and try to tease out some information, some generalities that we can think about. And before we start talking about the properties of sets of solutions, we need to get a little bit of vocabulary down. So we're going to take a look at this example. 6, 2, the ordered pair 6, 2 can be thought of a point in the xy plane. But another way of thinking about it is as a vector. So another way of thinking about 6, 2 is as a vector. Oops. And we've sort of seen this in section 1.1. So what do I mean by that? Well, if we think of the point 6, 2 probably be right around right here, maybe. No, that's a little too high. Let's go, how about right about here? That's more like it. Okay, so this, like we say, is the point 6, 2. But also you can think of a vector or a straight line going from the origin to this terminal point. And so that's what we'll call each of these. We've got this terminal point here. And we have an initial point at the origin. And this whole thing is called the position vector. And say that we call the point 6, 2 A, and the origin we'll call O. Then we could write the vector as O, A, and often we'll put a little half of an arrow on top to indicate that it's a vector. So let me give you one other definition. This is really going to be the subject of this section, or the meat of it. R2 is the set of all ordered pairs of real numbers. So R2 is the set of all ordered pairs of real numbers. So any two real numbers in an ordered pair is a member of this set. So for example, we'll see something like, obviously 6, 2 is in this set. And another ordered pair that could be in this set would be -1, 0. Another one would be maybe 5/2 pi. There's infinitely many. And sometimes we write these not just horizontally, but as column vectors like this. So we'll also see this notation. Okay. So just like we had ordered pairs in R2, R3 is the set of all ordered triplets. And so some examples of elements in R3 would be 1, 2, 3, or the ordered triplet -5, 4, 7, or the ordered triplet something like 3/2, 1.72, -e, just as long as the elements are real numbers, and there's 3 of them together, then they belong in R3. These we can also write as column vectors. So you'll see them sort of both ways. 1, 2, 3, 5, 4, 7. 3/2, 1.72, -e. So just like we could also have like R4 with 4 elements, or R5, R6, R7. And so we can really have any Rn where it's the set of all ordered lists with n elements of real numbers. So Rn is the set. So a set is just a group of objects, the set of all ordered lists with n elements of real numbers. And we'll get a lot of good practice with this. Okay, we know Rn is an idea that we definitely want to remember and get down really well. And now we're going to talk about 2 operations that we'll do quite a bit on Rn. And the first one is vector addition. And vector addition is what it sounds like. You're going to take 2 vectors and add them together. So let's look at an example and then we'll generalize it. Say that we had the vectors 2, 3 plus the vector 4, -1. So think in your mind, where do these vectors live? They live in R2 because they're pairs of real numbers. And to do vector addition, you just are going to add each element. So the 2 is going to get multiplied by the 4. No, sorry, 2 is going to get added to the 4. And so we get 6 up here, and then the 3 and the -1 are added together, and we get 2. And that's the answer. That's how vector addition works. So in general, if you have a vector u, and it can be any size of Rn, so maybe you start with u1 and you go all the way down to un. And you have a vector v, has to be the same size, v1 all the way down to vn. And you want to add these 2 together, so the vector u plus the vector v, you just add each corresponding element. So u1 plus v1, keep going down the row, and then un plus vn will be the last one. And this is how vector addition works. The other operation that is going to be a big deal in Rn is, it's not vector multiplication, but it's called scalar multiplication. And this is going to be where we multiply a vector by a real number. So scalar multiplication, think for a minute how you think this should work. Well, say that we have the vector 3, -2 sitting in R2, and we're going to multiply that vector by 5. Then you take each element in the vector and multiply it by 5. So 5 times 3 is 15. 5 times -2 is -10. And that's how scalar multiplication works. So if C is some scalar, which is just another word for real number, the word scalar just means real number. If C is some scalar, then C times the vector u. So these are two very different things. One is a real number and one is a vector. But we'll define scalar multiplication as you take the C times that first element and all those little elements. It gets multiplied by all of them. Okay, those are the two operations that we're going to focus on. Let's look at another example. So say that we have let u equal, here we're going to be in R3, 4, 7, -2. And we're going to let v, the vector v equal 1, 0, -1. And we want to find 3u plus 2v. Okay, 3u is just going to be 3 times multiplied by every element in the vector u. So 12, 21, -6. And to that we're going to add 2 times v. That should look like 2, 0, -2. And now we add those together. We get 14, 21, -8. Now, this right here, 3u plus 2v, has a name, and it is called a linear combination of those vectors. Anytime you add some multiple of a vector to another vector, or more than 2 vectors even, you're creating a linear combination. This is a word, a phrase that we want to remember. We'll see that again. Okay, now we have a new term that we need to talk about, closure. So we've talked about what a vector is, what Rn is, linear combination, and now we talk about the idea of closure in a set. So Rn is closed under addition and scalar multiplication. What this means is these two operations will always give you something back in Rn. So these two operations will always, your end result will still be in Rn. Give you something back in Rn. If you add 2 elements of R5, you're going to get another element of R5. If you take a scalar and multiply it by some element of R7, you're going to stay in R7. It's not possible for you to pop out of R7 into like R8 just because you added 2 vectors from R7 together. You'll stay in that set. So let me give you a counterexample of a set that's not closed. And that would be, so think about this set. So this is going to be a set that is not closed. I'm I'm going to give you a 1-element set, and it's the set 1, 0. Why do I say this is a set that's not closed? Well, if you take the element and add it to itself, you get 2, 0, which is not in the original set. You've popped out of our original 1-element set. And so that's why we say that this set here is not closed, but Rn, which is an infinite set, is always closed under addition and scalar multiplication. Okay, we want to talk about an important example. Sometimes you're asked to figure out if a certain vector is a linear combination of other vectors. And when you first see this, you may not know exactly how to solve something like that. So, for example, we could be asked, is the vector 7, 9, 15 a linear combination of the vectors 1, 1, 2, 1, 2, 1, and 2, 3, 4. And so I look at this vector and these 3 vectors, and I can't tell right away if we can get this vector by adding some multiples of these vectors together. That would be what a linear combination means. So if I can't just look at it and tell, then I try to think of a way to set up an equation that would mean that 7, 9, 15 is a linear combination of these other 3 vectors. So if it is a linear combination, it means that this is equal to some multiple times this, plus some multiple times this, plus some multiple times this. And the way that that would look in an equation is that 7, 9, 15 is equal to some constant, we'll call it C1, times 1, 1, 2, plus another constant, we'll call it C2, times 1, 2, 1, plus some constant C3 times 2, 3, 4. So if it's possible, then this equation has to be solvable. Well, this equation I can't solve just by looking at it either, but I'm going to do something I know how to do, and I'll multiply those constants into those 3 vectors. So this equation is also saying that 7, 9, 15 equals, let's see, that would be C1, C1, 2C1 plus C2, 2C2, C2 plus 2C3, 3C3, 4C3. I just multiplied those constants into each of those vectors. Things are starting to look a little clearer because I can actually take these 3 vectors and add them together, and I'll just get one nice ordered triplet. So let's do that next. So I'll still write 7, 9, 15 must equal, let's see, I've got C1 plus C2 plus 2C3. C1 plus C2 plus 2C3. That's just one real number. And then the middle element will be C1 plus 2C2 plus 3C3. I'm just adding the corresponding middle elements from each of these vectors. And then the last part will be 2C1 plus C2 plus 4C3. Okay, So that looks pretty good. And now I know if this vector equals this vector, that means that I could have, if I can find some numbers C1, C2, C3 that make all of this work, then that means that the first triplet is a linear combination of these guys. So let's see, 7, because these two vectors are equal, 7 has to equal this first element, and 9 must equal this, and 15 will equal this, which sounds to me like 3 equations in 3 variables, and that's definitely something that we can solve. So 7 would have to equal C1 plus C2 plus C3, and 9 would have to equal C1 plus 2C2 plus 3C3, and 15 would have to equal 2C1 plus C2 plus 4C3, because these corresponding elements have to be equal. Whoops, definitely didn't need that. Yeah. Okay, I'm going to take this system of equations now and solve it. Correction, this right here needs to be 2C3. I've put this system of equations into a matrix and then had my calculator do the reduced row echelon form, and this is what I got out, which is awesome because I can see that we have a solution. That we've got what, C1, here's our C1, here's our C2, and here's our C3 just sitting here. So let's just double check that that's actually correct. Let's say it like this. Does 2 times 1, 1, 2, so that would be the C1, plus negative 1 times 1, 2, 1, so that's C2 times the second order triplet, plus 3, which is our C3, times the third order triplet. Okay, let's see what that would equal. We've got 2 minus 1 is 1, plus 6 would be our 7. That's good. Then 2 minus 2 is 0, plus 3 times 3 is 9. And 4 minus 1 is 3, plus 12 is 15. Looks like it works out. That was just a double check, but that our original order triplet, yes, the answer is we can write it as a linear combination. And in fact, we say exactly how it is written. The reason this is such a good problem is because it ties in a lot of ideas that we've talked about in these first 3 sections. At some point during the problem, we had to solve a system, but the whole problem starts out by talking about the idea of a linear combination and these vectors or these ordered triplets that sit in the subset R3. Last thing before we leave section 1.3 is we need to talk about the properties of vector addition and scalar multiplication. Commutative property, you can reverse the order of the two vectors. Associative property, you can group them in different ways. Property of the zero vector, adding the zero vector, which like in R2 the zero vector would be 0, 0. In R3 it would be 0, 0, 0. Doesn't change the original vector. Property of the negative vector. Distributive properties still hold when you're doing scalar multiplication, and then scalar multiplication by 1. So you are asked in the homework to prove one of these. I can't remember which one, but on page 30 at the bottom are some good examples of how to go about proving that. All right, it was a great section.